Okay, so today we're gonna teach you about torque on a current carrying wire. So first, we're gonna have to investigate first the forces acting upon the loop. So first, we're gonna have to investigate. So as we know, the force on a magnetic field is equal to the magnetic field acting upon and the current that is flowing.
So, on the loop that is shown on the video, if the current passed through here, going to the left side, and if the magnetic field is flowing to the right side, there is no force. Why? This is because the angle in between the both of them is 180, like this. And as we know, sine 180 is equals to 0. So with this, force is equal to ILB sine theta. The force would be cancelled out on both sides. The same goes to the top part. It also has no force because it is sine 0. And sine 0 is equals to 0. So the only thing that we should put our attention on is this current that is flowing upwards and this current that is flowing downwards. The magnetic field is going to the right side, the current is going upwards. So if we notice here, on the right hand rule, the fingers are facing to the right, which represents the flow of the magnetic field. And the direction of the curl, which represents the current, is pointing upwards. We could see that the thumb, which represents the force, is pointing outwards, so the force is out of the page. Then at the other side, the force is just the opposite of the first side. Let's try applying the right hand rule. So the magnetic field is going to the right, then the current is going downwards. And notice that our thumb is pointing into the page. So as we can see here, we have two forces, out of the page and into the page. And this would explain that the summation of our forces are 0. Why? Because the first one is going outwards while the other is going inwards. Therefore, it wouldn't move. But if you think about it, if this part is going outwards and this part is going inwards, the force is going on a circle. And this is what we call the torque, the rotation of something. Then, this is the axis of rotation. So, how are we going to get the torque? The next thing that we have to analyze is the formula of the torque. And to do this, we have to look for the area at this side. So let us label this first as B, and this one as A. To get the area of this part, this would be B over 2 because this is only the half of this part. So the things that are acting upon this are the current, magnetic field, and the length. So the formula would be IBA. And since we have two forces acting upon this example, the force that is out of the page and into the page, we have to put 2 here. Then we add sine theta because it is a vector. So all in all, the formula of the torque would be torque is equal to I times B times A times sine theta. So, why is it area? Because this part is length times width. So there you have it. Here are some sample problems.
First, write the given. N equals to 200 turns. And then B, or the magnetic field, is equals to 300 microtesla. Our theta, or angle, is equals to 30 degrees. Our I, or current, is equals to 3 amperes. And then we will look for the torque. We then write the formula, which is NIBA. And then, since we don't have the A, or it is not given, we will solve for A, wherein the formula for the A, or the area, is pi r squared. And then we will substitute pi, and then we will look in the given again, and then we will convert the 2 into 0.2 meters, and then square it and multiply to pi. The answer is 0.126 meters squared. Now we have the area. Next, since we have the N, the I, the B, and the A, we can now solve for torque. And then, oops, I'm sorry, I forgot the sine theta. We will add the sine theta in the formula. I'm sorry for my mistake. The formula again is NIBA sine theta. Now we substitute the given. N is equals to 200. I is equals to 3 amperes. B, the magnetic field, we will convert it again, or we will make it 0.003 Tesla. And then the A, what we solved earlier, will be 0.126. And then sine theta, or 30. Sine 30. And then if we will input this in the calculator, we will find the answer 0.113 Newton meters. And then this is our torque. We'll box our final answer, and that's it. Simple as that.
So the question is given to us is to find the magnitude of its magnetic dipole moment and find the torque and potential if the dipole is oriented at 30 degrees considering uniform magnetic field magnitude is 0.50. We have the given radius, which is 2.0 cm, and we have a current of 2.0 m. Now, let's solve for the magnitude of its magnetic dipole moment. First, let's write the formula of the magnetic dipole moment, which is mu is equals to I times A. When we put in the values that we are given, we get 2.0 times 10 to the negative 3 amperes times pi times 0.2 m squared. Once we input this to our calculators and calculate it, we get the value 2.5 times 10 to the negative 6. Now, let's solve the second question, which is finding the torque and the potential if the dipole is oriented at 30 degrees. First, let's write the formula that we use, which is torque is equals to mu times magnetic field. This can also become mu times magnetic field times sine 30. If we add in the given, we get 2.5 times 10 raised to negative 6 m squared times 0.5 times sine 30. And if we calculate that, and in our calculators, this is equals to 6.3 times 10 raised to negative 7 with a unit of n times m. And now we're moving on to the third question, which is finding the potential. Let's solve the potential using the formula negative mu times magnetic field times cosine 30. If we input our data, we get negative 2.5 times 10 to the negative 6 m squared times 0.5 times cosine 30. From this, if we calculate this in our calculators, we get the answer 1.1 times 10 to the negative 6 with a unit of joules.
Magnetic field lines indicate the direction of the magnetic field in space. Magnetic field lines does not end on magnetic poles, but they form closed loops instead. Magnetic force is the consequence of the electromagnetic force, and it occurs whenever the objects interact in which there is charge in motion. The magnetic force on a particle with a charge q moving with a velocity in the magnetic field is given by this. We can use this formula, but this is written in the vector cross product. So we can write the magnitude of the magnetic force by expanding the vector cross product by using this formula. The direction of the force depends on the relative direction of motion of the charge in each case. The magnetic force on the current carrying conductor is perpendicular to both the wire and the magnetic field with the direction given by the right-hand rule. Right-hand rule gives the direction of the force. We can use our right hand, and the fingers points to the direction of the magnetic field and the thumb points to the direction where the positive charge moves and the direction of the current. Factors affecting the magnetic force on a current carrying conductor on the magnetic field are the length of the wire, the current flowing through the wire, and the strength of the magnetic field. The magnetic force on the current carrying conductor is given by this, wherein I is the current, L is the length of the straight conductor in a uniform magnetic field B, and theta is the angle between the I and B.
Example number 1. We will find the given. So the given are magnetic field 1.50 Tesla, current 20 ampere, length 5 centimeters. We will convert the length into meters, so it will be 0.0500 meters. Then the force can be found with the given information by using the formula F is equals to current times length times magnetic field times sine theta. Note that the angle between the I and the B is 90 degrees. So the sine theta is equals to 1. So we will now enter the values in the formula. So it will be F is equals to 20 ampere times 0.0500 meters, 1.5 Tesla, and 1. We will use a calculator. So 20 times 0.0500 times 1.5 times 1. 1.5. 1.5. For the unit, 1 Tesla is equals to Newton over ampere meter. So we will cancel ampere, meter, and Tesla. And the remaining is Newton. So the unit is Newton. And the final answer is 1.5 Newton. Example number 2. We will find the given. The magnetic field is 0.50 Tesla, the current is 20 ampere, the length is 0.10 meters, and the angle between the I and B is 60 degrees. And we will use the formula F is equals to I times L times B sine theta to get the magnitude of the force. We will enter the values. So F is equals to 20 ampere times 0.10 meters times 0.50 Tesla times sine 60 degrees. 20 times 0.10 times 0.50 times sine 60. 0.866. So, for the unit, 1 Tesla is equals to Newton over ampere times meter. Cancel the Tesla, ampere, meter. And the unit is Newton. So, the final answer is 0.87 Newton. Example number 3. Here are the given values in example number 3. The magnetic field is 50 Tesla, the current is 10 ampere, the length of the wire is 0.20 meters, and the theta, or the angle between the I and the B, is 30 degrees. So we will use the formula, this formula. We will insert the values. F is equals to 10 ampere times 0.20 meters times 50 Tesla. And we will use the sine 90. We will not use the 30 degrees because the wire is perpendicular with the magnetic field. So we need to be careful with the angle. And we will input it in the calculator. 10 times 0.20 times 50 times sine 90. 100. So the answer is 100 Newton.
Doon nakapos tayo ba?
Wow, gabo. Dali na to.
Sariling sikap ko.
Ganyan. Tapos, so ikaw na lang mag-English. Explain ko na lang. Sige.